All right, good morning, guys. It is Wednesday, May 27th. We're going to do the conservation of energy practice problems. All right, so here we go. Question one, what does the law of conservation of energy state? Pretty simple. The energy in the universe has to remain constant. And in a closed system, the energy before the event is going to be the same as the energy after the event. Anything that brings up the idea of conservation. Energy can change forms, just the total amount has to remain the same. All right, two. So if a ball is thrown straight into the air with an initial kinetic energy of 100 joules at the top, what kind of energy would it have and how much? Oh, I'm sorry. So it's thrown at 100 joules, and at the very top, what kind of energy will it have and how much energy will it have? Okay. Well, right back to question one. If it's a closed system, which this basically sounds like it, that means the energy in the beginning has to be the same as the energy at the end. So if the beginning is at the bottom and the end is at the top, it'll have 100 joules of energy at the top. What type of energy will it have at the top? Well, it's no longer moving because if it's at its highest point, we know there's no velocity, therefore the kinetic energy would be zero. So all of the energy has to be potential energy, and it's potential energy due to gravity. Letter B, if the ball lost 5% of its energy due to air resistance, how much energy would it have at the top? Okay, so if it started with 100 joules of energy, well, 5% of 100 joules is 5 joules. So if it loses 5 joules, that means it started with 100 joules, and at the top it now has 95 joules. And that would be an open system where energy can move in from the surroundings to the system, or energy can be taken from the system to the surroundings. All right. Okay. So a ball with a mass of 2 kilograms is thrown straight upwards with an initial velocity of 14 meters per second. The ball only reaches a height of 8 meters instead of 10 meters because of air resistance. Is the work of the air resistance positive or negative? All right, so for the first part, we can just answer this. We know air resistance is like friction. It always kind of works against you, so it's negative work. All right, it's going to be taking work out of the system. B, how much work does the air resistance do? All right, so now we need to solve a problem here. So solve this, all right, before and after. So in the beginning, all right, it doesn't say, so we can assume we're starting on the ground. If we're starting on the ground, that means potential energy due to gravity is 0, okay? There's no elastic potential energy anywhere in the problem. I'm not even going to write it. So the only energy we have in the beginning is kinetic. That's 1/2 of mv squared. So 1/2 times 2 times 14 squared. Okay. Well, we just said that there's another initial source of work. It's friction. So we know friction is going to be, it's going to do negative work. So we're actually going to still make it positive. And then our answer will be negative. You could make this negative and then just take the value you get. It doesn't really matter. All right. Oh, this should not say force of friction. This should say like work of friction. All right. And then on the right side, we're at our highest point. So if we're at our highest point, the only energy we're going to have is actually potential energy due to gravity. There's no kinetic energy. So it's mgh again. So the mass of the ball is 2. It only reaches a height of 8, 9.8. All right, so if we solve, right, on the right side, we're going to get 14 squared, because half of 2 is 1, so that's 196. Two times 8 times. All right, I will be right back. All right, sorry about that. Okay, I am so sorry. I have to do this again. I apologize. Issue in my son's room. Okay, so we'll do this again. So we starting with it's all kinetic energy we said. So that's 1/2 of 2 times 14 squared. We said that was 196. All right, equals on the other side was mgh. So that's 289.8. That was all of the potential energy due to gravity to 156.8. All right, so there's got to be something here that's taking away work. So we can just say, right, that was the work of friction. All right, so if we solve for the work of friction, we divide it, or I'm sorry, we subtract that number over, so minus 196, and we get the work of friction, WF, is negative 39.2. And that makes sense. We said it was going to be negative. How much work does it do? We found it out. It does 39.2 joules worth of work against the system. And then how much force does the air resistance have? Okay, well, we know this. We know work equals force times distance. So we can, we actually don't need the negative sign here. Let's ignore that. So work equals force times distance. We're looking for force. And the distance, well, how high did the ball travel? It traveled 8 meters, so the distance is 8. So we divide both sides by 8. 4.9 newtons of force, or negative 4.9 newtons of force, really. That's how much is done by the air resistance. All right, last problem. So Zach has a swing set with a matching 4N slide. One at the top, he's 2 meters off the ground. If he starts from rest, what will Zach's velocity be at the bottom of the slide with no friction? Okay, so we're gonna do this the same way as before. So he is starting at the very top of the slide, right? And he's at the top of the slide, and it says he starts from rest. So if he starts from rest, there is no kinetic energy in the beginning. There's no elastic energy anywhere in the problem. So initially, all of Zach's energy is gravitational, right? And at the bottom of the slide, he's at the ground. So there's no gravitational potential energy, but he's moving. So it's all kinetic energy. All right, so this breaks down to mgh, 15 to 9.8. All right, and then equals 1/2 mv squared. All right, so if we solve, (6.26). All right, I have to take the square root and say 6.3 meters per second. Okay, that's for A. B, if Zach's slide actually produces some friction and now there's 50 joules of friction produced, all right, what would Zach's velocity now be? So we have the same basic idea as before. At the beginning, all the energy is potential. At the end, it's all kinetic. The only difference is that we have this friction again, right? Friction always works against us. It's a negative force. So I'm just going to put it out front. The same idea. And then that friction is going to be negative. So work of friction. All right, and now we'll just plug everything in again. So we had 15 times 2 times 9.8. And that's 294. So we have negative 50 plus 294 equals on the other side half of mv squared, which is a 7.5 v squared. All right, so 50 minus 294, or actually, I'm sorry, negative 50 plus 294. I have to have a positive answer there, is 244. And then when we solve again, we get 5.7. And if we look at the two answers, right, they make sense. In blue, that was Zach's velocity with no friction. So he is basically having the benefit of all of the work that's potential becoming, or all the energy that's potential energy being transferred into all kinetic energy. Nothing is lost. In the second part, which is in the green, right, there's this additional force. Work is stealing some of that energy. It's taking it from the system to the surroundings, right? That lowers the available energy that can be transferred to kinetic energy. And then at the end, Zach isn't going to move as fast because he doesn't have as much kinetic energy available to him. All right, so these are the 4 conservation of energy problems. I hope you did really well. I hope you didn't need this review at all, but if you did, I hope it worked out for you. And if you have any questions still, please don't hesitate. Shoot me a reminder, let me know what's going on, and I'll talk to you guys later. See ya.